Okay, let's pick up where we left off. For this last function, the degree of the numerator was 3, the degree of the denominator was 2. Since the numerator was greater than the denominator, the theorem says there's no horizontal asymptote. Okay, so definition, don't worry about this part. Next thing, when you're graphing these, you must mark your asymptotes as dashed lines on your graph. So this first one has a vertical asymptote at -1, mark it with a dashed line. Horizontal asymptote at 2, mark it with a dashed line. This one has no verticals, but it has a horizontal at 0, mark it with a dashed line. Same thing over here, vertical at 1, dashed line, horizontal at 0, dashed line. So we have to do that first when we're graphing. Okay, I didn't particularly like this problem, so I'm skipping it. And so let's go and graph. So to graph a rational function, you want to find the asymptotes, the intercepts, mark those on your graph, then use your calculator to place the curves. So we did all the information for these before. For x plus 4 divided by x minus 2, we had found the vertical asymptote. Remember, it comes from the 0 of the denominator. We had found the x-intercept, comes from what makes the numerator 0. We found the x-intercept, the y-intercept, which one is that? The y-intercept by letting all the x values be 0. And the horizontal asymptote is at 1 because the degree at the top is 1, the degree at the bottom is 1, so we take the coefficients divided by each other. Now let's take all that information and put it on a graph. So we've got a dotted line on the vertical, we've got a dotted line on the horizontal at 1. Let's plot the x-intercept is at -4. So over here at -4. And we got a y-intercept at 2, so let's come down here at 2. Okay, that's all the information we have. So when we go to our calculator to graph that one, let me come over here and turn the rest of these off. Okay, enter, turn him off. Quit. Okay, whatever. I'm not sure what you want me to do here. Okay. Okay. Great. I want a line. Clear. Done. I want to go up here. Okay. Press enter. Maybe if I press enter. There we go. I don't know what that meant. However, I want to go over here and press enter and turn him off. Then I'm going to go up and press enter and turn him off so I can only graph the one at the top. Okay, so here is the graph of that function. And look at your paper. So I've got two curves. The one I'll place, kind of hard to make that smaller. Let's see if I can make it smaller. There we go. So now let's place those curves. You see the one on the left? It's going to go through the 4, through the 2, and follow those asymptotes. Follow the horizontal up, follow the vertical going down. And the other curve is going to be in the upper right, and it is going to follow both of these asymptotes. Your curves must approach these asymptotes and never cross the vertical asymptote. So for the next one, the vertical asymptotes were 2 and -2. We found those from the denominator. What made the denominator 0? X-intercept came from what made the numerator 0. Y-intercept, we put zeros every place for x. And the horizontal asymptote, since the degree at the top was equal to the degree at the bottom, it was 2 over 1, which is 2. Now, I've marked those asymptotes, positive 2, negative 2 for the vertical, and then 2 for the horizontal, and the x and y intercept is here at 0, 0. Now let's go to the calculator and figure out our curves. So let me come over and take him off and turn him on, and let's graph him. So we see we've got a parabola piece in the middle, and then 2 curves meeting those asymptotes on the left and the right. So we kind of have a parabola thing in the middle, and then 2 curves, one here at the top, one here at the top. Kind of got a little messy, but use your calculator to place your curves. And let's do this last one. Remember, it didn't have any vertical asymptote because there was no real number that made the denominator 0. X-intercept, the 3, made the numerator 0. Y-intercept, if we let all the x's be 0, we get negative 1/3. And the horizontal asymptote, because the degree at the top is 1, the degree at the top was 2, and since the numerator was less than the denominator, it's y equals 0. And I've got that guy marked over here. So let's see what the graph shows us. So we just see the slight little graph running below the x-axis. It eventually crosses the x-axis and goes above. So let's see how we can do that on our graph. We had a y-intercept at a negative 1/3. That's going to be down here. And an x-intercept at 3, which is going to be, let's say that's 3. And that's my 1/3. Negative 1/3. So what we saw graphically was the graph coming from the left, kind of made a little downward thing, and then goes up on 3, and it just hovers above and below that horizontal asymptote. That one's a little tricky. So that's graphing your rational functions. Let's take a look at an application. So we've got population growth. 100 deer are introduced to a newly acquired state game land. The population N of the herd of deer is modeled by this particular function. Time represents years. We want to graph it, find the populations for certain values, and determine what is the limiting size of the herd as time increases. So let me pause for a second. Okay, so let's look at the graph on my calculator. I want to show you the window. And here is the window I used. X-min was 0, X-max was 100, Y-min was 100. My dog is eating food. Pee-wee! Quit. Y-min is 100, Y-max is 1500. If you use that window, you will get this nice graph. So there is our graph representing the number or the population of deer. And the first thing is, let's find the population when T is 5, T is 10, and T is 25. So we can just go to the table feature. We can go to second calc and choose that value feature. And so let's type in T equal 5. Okay, so we get 33.33. I think it was 333.33 when T is equal to 5. Okay, let's type in 10. So when it's 10, we've got 500. At 10, we've got 500. And then let's see what happens at 25. We have 800. So, yeah, it looks like the population is increasing as the number of years goes on. The next question is, what is the limiting size of the herd? It can't increase infinitely without bounds, so let's see what the calculator tells us. Yeah, it appears that this thing is sort of tapering off. So let me go a little bit further on the x-axis. Let's make the x max to be, 300. Let's see what that does. I see it's tapering off. So let's hit this trace button and let's trace to the right and see what is that y value we're getting. As we go further and further to the right, that y value's approaching some number. Let's keep going to the right. $13.85 right now. What I want you to realize is that it is approaching the horizontal asymptote. The horizontal asymptote gives you the limiting size of that herd. Okay, so then let's come back over here and see if we can figure out this guy's horizontal asymptote. So I am going to actually rewrite this as a 60t plus 20 times 5 is 100. So all I did was distribute the 20 and put the variable first. I'll put the variable first here as 0.04t plus 1. And if I want to find the horizontal asymptote, since the 2 degrees are equal, it would be 60 over 0.04. That's where our horizontal asymptote would be. Y equal to 60 over 0.04. All right, let's find that number. 60, let's clear that out. Okay, 60 divided by 0.04. Our horizontal asymptote is at 1500. So that is the limiting size of the herd. If I went back to my graph and went with my window and made my X max a little bit bigger, like 500, and if I traced along to the right, those Y values should be getting closer and closer and closer to 1500. Is that what it looks like? Yeah, they're getting close to 1500. So that horizontal asymptote is your limiting size of your herd. The herd can only get so big, and then again, there becomes a lack of resources and disease, and they'll just die off. But you see, it's getting closer and closer to the 1500. And you could continue to show that it doesn't go beyond 1500. So here's an example of a rational function that's showing growth over a particular time of deer that were introduced into a newly acquired state game land. Hope you don't have any questions on that. There is one more here, which is similar. You've got a moth that's consuming some food. And the question is, at what level of consumption will the moth be satiated? You can kind of play around with that one. I'm not going to work it out because I am running out of my 15-minute time slot. So I think you have enough information to be able to get through the homework and get through the 2 problems that I sent you home with that are due on Monday. So have a great weekend. I'll see you in class.